Guys, welcome back to chapter 12. Today we are going to continue our discussion of entropy, and today we're going to quantify that. So we're going to be able to put some numbers to what we've been talking about. So in the last video we ended with the following idea, that the third law of thermodynamics tells us that if we have a perfect crystalline structure at absolute zero, that the entropy of that substance would be zero. Now, absolute zero doesn't exist. That's hypothetical at this point. And a perfect crystalline structure, well, perfection is hard. So what that tells us is that anything that is above 0 Kelvin or is an imperfect structure will have an entropy value of greater than 0. Now, a lot of experimental data has been collected for different substances. So we can calculate, and we're going to calculate, standard entropies. So standard entropies are when we are in standard conditions. Standard pressure, 1 atm. Standard temperature, 25 degrees Kelvin. So it's possible for us to determine the entropy of a particular substance. And then we'll take that one step further and look at the entropy as it changes across the chemical reaction. So standard molar entropies, this little degree symbol is just an indication that we're using standards. So we're going to look at some tables that are from experimental measurements, experimental data, but they threw them into these tables and now we can use them as standards. So these values are based on standard conditions, so 1 mole of a substance at standard pressure, standard temperature. If it's an aqueous solution, the standard is a 1 molar concentration. And then finally, we're going to use these values. We'll look at a table in just a second. But finally, we're going to use these values to calculate the standard entropy change for a particular process. So this delta symbol is just the symbol for change. And again, this degree symbol is just for standard. So we're going to look at some final time, some initial time, and then how does that entropy change? So final minus initial. Here's an example of a table of standard entropies. So again, these types of values will always be given to you, not something you're going to need to memorize. But we just see, all of these values are positive, right? So they've got to be greater than 0. You've got some values that are very small, some values that are a lot larger, just depending on the potential energy of that particular substance. One thing I want to point out, the units here are kind of wonky, but when we start to do math, they'll work themselves out. So the unit for entropy is joules over mole Kelvin. Okay, so that is not a formula, that is the units. So it is a measure of energy. That's where we get the joules per mole. So that's part of the standard portion of this. And then it is temperature dependent. So Kelvin is in there as well. So how do we calculate the entropy change for a particular system? So let me just talk about what we're symbolically representing over here. So this is just the change in energy, so that denotes change in entropy, and this is our shorthand for reaction. So we're looking at a chemical reaction. Just with the equation tools, this is kind of floating out here. If I were to handwrite it, I would write that degree symbol maybe a little bit closer. But that is just, again, standards. We're going to use standards to determine this. So change in anything is always final minus initial. So it doesn't matter if we're tracking change in finances, change in weight, change in entropy. We're always going to take final minus initial. Now, when we talk about chemical reactions, we don't typically talk about final and initial, right? When we talk about a chemical reaction, we often talk about reactants and products. So when we're looking at the entropy change for a given reaction, we're going to look at the standard molar entropy for the products minus the standard molar entropy for the reactants. So that is our final and that is our initial. Okay. Now, in chemical reactions, often we don't have just one product and one reactant. Often we've got multiple. So when we're doing the standard molar entropy for a reaction, we are going to take the sum of all of the products. So this fancy symbol here is just the symbol for summation of all of the entropies for the particular products. And then we're going to subtract that by the sum of the entropy change for the reactants. Okay, so that's just saying if we've got something like A plus B produces C plus D, we'll take the entropy change for C plus the entropy change for D, and that would be our products. Okay. Now I left a gap in here because there is one more thing that we need to add to this. And we don't want to know the standard entropy change for multiple, or for just one mole of a given substance. So let's say this was 2A reacts with 3B to produce 3C and 2D. We've got to make sure that we're taking into account how many moles of each of these substances is produced or consumed. So the last thing that I left out here was this N value. So this N value just takes into account the number of moles that's being created or the number of moles that's being produced. Okay. So for this particular example, we would take 3 times the standard entropy for C plus 2 times the standard entropy for D. That would be this first value. Then we're going to subtract that from 2 times the standard entropy of A plus 3 times the standard entropy of B. And then that would be our second value here, and then we would subtract those two. Okay. So here is, let me get all this stuff off. Here's kind of the official formula for this entropy change. We've done this before with enthalpy, so technically this is a little bit of a review. I think the best way to attack these problems to really understand what the heck this formula is just to dive into an example. So that's exactly what we're going to do. So here's a table of standard molar entropies for different molecules. And we want to calculate the change in the standard molar entropy for the following reaction. So what we're going to do here is to get the change in entropy for this reaction, we are going to figure out the change in entropy for products, and then we're going to figure out the change or the entropy for our reactants. We're going to take the sum of those and eventually subtract them from one another. So I like to start by determining the products, just as a reminder that that's going to be the first one, that minus the reactants. So that's what we're going to do here, is we're going to determine the entropy change for the products. Okay. So first, we are going to have our entropy change for NO. So the entropy change for NO is 210.8 joules per mole Kelvin. Then I need to acknowledge how many moles of that is being formed. So I look at the coefficient and I multiply that by 4 moles. Okay, so this is the entropy for 1 mole, but we're making 4. And then I'm going to add that to the entropy of water, which is 188.8 joules mole Kelvin. And then we're making not 1 mole, but 6 moles of water. So I'm going to multiply that by 6. All right, so I'm going to clean up each side of this equation. Grabbing my calculator. All right, so for the first variable here, we're going to take 210.8 times 4, and we get a value of 843.2. Now let's take a look at the units here. I've got a mole on top. I've got a mole on the bottom, so those cancel. And we're left with joules over Kelvin. And now I'm going to do the same thing for the second variable, 188.8 times 6. Our unit of moles falls out. And this value is 1,032.8 joules over Kelvin. So to get the sum of the entropy changes for the products, we're going to add those two values together. So 843.2 plus 1132.8. And the entropy change for the products is 1976 joules over Kelvin. So that was just for the products. That's one part of this. Why don't you guys go ahead and pause the video and see if you can determine the sum of the entropy change for the reactants. And then I'll catch up with you on the other side. All right, so we're going to do the entropy change for ammonia first. I'm just going to change colors here. So we've got 192.8 joules mole Kelvin. And we're not making 1 mole, we're making 4 moles, or using 4 moles. So moles cancel. Then we're going to add that to the entropy for oxygen. So that is 205.2. And we are not using 1 mole, we are using 5 moles. All right, so plug this into our calculator. We've got 192.8 times 4. So that's 771.2 joules over Kelvin plus 205.2 times 5, which is 1026 joules over Kelvin. So then we're just going to add those two values together. So 771.2 plus 1026 equals 1797.2 joules over Kelvin. All right, so we've determined the entropy change for the reactants. We've determined the entropy for the products. Now we need to look at the entropy change for this reaction. So to determine the standard molar entropy change for the reaction, we're going to take the entropy for the products minus the entropy for the reactants. So if we click back, products was the first one that we did. The entropy change for the products was 1976. So 1976 joules over Kelvin. And then we are going to subtract that from the entropy change of the reactants. That was the second one we did. So the entropy change for the reactants was 1797.2. Is 1797.2. So the entropy change for this reaction equals 1976 minus 1797.2, and we get a value of 178.8. All right, well, what does this mean, and does it make sense? So I always want to teach you guys, does this make sense? And it's not just a number, it actually means something. So in this case, the change in entropy for this reaction is a positive value. Okay. So does that mean things are getting messier or they're getting more organized? Yeah, messy is a good thing, right? Things automatically get messy. So we're increasing the mess, increasing disorder, increasing dispersion, right? So now let's go back and look at the equation and see if we can see this make sense. So looking at the balanced chemical equation, what can we deduce about this increasing disorder? Well, all of the states are the same, so gas, 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 that doesn't change. There's no indication of like a temperature change here. Let's look at the number of particles. How many particles do we have on the reactant side? 9, right? 5 plus 4. How many particles do we have on the product side? Yeah. So we're increasing the number of molecules, which leads to an increase in entropy. So the more we have, the messier it gets. So the positive value for the entropy change makes sense to us, right? So we will do much more of these calculations throughout this chapter, but I hope you guys found this helpful.